So I think we can start now. So hello everybody, this is Luboš Pirkl from CFD Support. Welcome to the webinar about TCFD, the unlimited and focused CFD code. As you likely know, we recently released the new TCFD version 18.10, and TCFD is now again much better. And in today's webinar, we would like to show you how to simulate funds in it. I hope everything works well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and its recording will be later made available on our YouTube channel. And I guess this is it for the introduction. So I think we can start. So please let me start with the introduction of the webinar speakers. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support, and my current job is telling the world about CFD Support. And today I'm here with my colleague, Radek Máca. Hello, Radek. How are you?
Hello, Luboš, and hello to everybody who is watching. I'm fine, thank you, and I'm really looking forward for today's webinar. So, Luboš, you can continue.
Thank you, Radek. I only note Radek is our head engineer and senior developer here at CFD Support, and he will take care of the technical part of today's webinar. So we're looking forward to it. Okay, so this is the webinar agenda. The webinar is going to take about 1 hour. There will be 3 parts in this webinar. In the first part, there will be general introduction, which is this introduction. I'm going to point out the main TCFD features and capabilities. In the second part, Radek is going to give you a live TCFD experience. He's going to present it on a fun simulation workflow. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to ask your questions. Some questions will be answered right in the webinar. The rest of the questions will be answered via email, so you can be sure all the questions will be answered. Yeah, a few words about CFD Support. So CFD Support is a private engineering company dealing mainly with computational fluid dynamics. We are located in Prague, Czech Republic, and we deliver complete CFD engineering projects. We do various projects on demand all across the CFD field. We also deliver extensive OpenFOAM training and consultancy, as well as OpenFOAM support and custom code development. And of course, our flagship product is TCFD, which this webinar is about. So that brings me to TCFD. So please let me give a brief description. What is TCFD? So TCFD is comprehensive high-tech CFD code, which is focused and unlimited. It was designed to be a complete CFD workflow. It covers all the engineering steps from the pre-processing over the simulation run to the very detailed post-processing of the results. And it's independent on any other software, and on the other hand, it's fully compatible with the other software. So for this reason, it can be easily integrated into an existing process chain in any organization. TCFD is a unique CFD software because it's unlimited, which means our clients can keep TCFD forever. They can use it for an unlimited number of users, jobs, or cores. And this gives the investment in TCFD a permanent value. And also, this means our clients can scale their CFD simulations in a really, really big way. TCFD is focused on particular workflows. So, for example, a fun engineer uses the fun inputs, fun names, fun units, and fun results, as you can see later in this webinar. TCFD is automated, so for this reason, TCFD workflow is extremely effective, and also the automation reduces the chance of human error, which is also very important. TCFD has very good technical support. We keep custom approach to every customer, to every issue. We never leave behind any of our clients. We are flexible in it, and we support our clients even in matters out of the CFD field, for example, in numerical mathematics, physics, IT, or even software engineering. The real tutorials are available. So currently there are 22 tutorials that are based on the real machines and on the real projects we solved in the past. So the new TCFD user has no doubts about how to start and even what's the best practice settings. Yeah, TCFD is very progressive because it successfully merged the benefits of an open source, which means it's perpetual, unlimited for users, jobs, and cores. It's flexible, it's customizable, and it merged the benefits of the open source and commercial code, which is usually professional technical support, graphical interface, which it's robust, accurate, automated, well documented, well tested, and ready for the industry. So it merged these benefits of commercial codes and open source. And also, the user can put simply the data in. The CFD does its job, writes down the results, and later, in the end, the user can just pick up the final report, and this is it. So TCFD can be either used as a black box, or it can be used as a fully sophisticated CFD code where all the options are open. So this is very important. So the beauty of TCFD is that it's the user who decides how deep to dive into CFD or not even at all. Okay. TCFD is always focused on particular workflows by particular applications. So TCFD core has always been turbo machinery simulations like pumps, fans, turbines, compressors, hydro turbines, or for example, wind turbines, and many other kinds of other turbo machinery, both radial and axial machines, both compressible and incompressible fluid flows. And later, we decided to extend what had worked so well in turbo machinery field to an external aerodynamics. So now TCFD is able to simulate cars, aircraft, or other external flow. It can also simulate the internal flows like valves or piping systems or manifolds and many others, or for example, ship hydrodynamics. So it's the usage of TCFD is very wide now. So these are the applications. There are a few technical details. I will go very quickly over them. So TCFD is natively compiled for Windows and for Linux. It's up to the user which workflow is used. They are exactly the same. 100% of workflow is in the graphical interface. The batch mode is available, so TCFD can be run by another software on background. TCFD is further scriptable in Python. What's important, the automated meshing system is included, or the external meshes can be loaded. The trial version is available, so anybody can try TCFD, and after he or she has tried it, you can decide whether to go for it or not. It's very transparent for this reason. The real tutorials are included. TCFD has strong post-processing. It has special reporting system in HTML format. Also, we have developed a special set of tools for turbo machinery post-processing. There's extensive documentation available, PDF manual, videos, how to work with TCFD. Many of the resources are available online. And maybe what's important to say, our further development is users driven. So we usually create a pool of questions and wishes of our customers, and then we implement them to the next releases. Okay. I will move forward in my contribution, and yeah, we have a few case studies we would like to show you and to show the TCFD performance. So I'm not gonna go for the details. I will just quickly go through them, and in case you would be interested, feel free to request the details. We will gladly provide all the details we can tell you. So I have a few benchmarks and validation examples I will show you now. So this first example is the benchmark of a simulation of the real existing radial fan for which the measurement data is available. It's a special radial fan benchmark project we did together with our partner ZVVZ Machinery. This particular radial fan is quite difficult to simulate. It has a wide impeller and it has a very complicated airflow, including low pressure ratio and combined together with a high flow rate. So this combination is very challenging to simulate for any CFD code. So we did both steady state and transient simulations, and we created complete fan characteristics, which you can see. So you can see there is a very good agreement with the measurement data. So that's fun validation study. In another project we did together with ČZ Strakonice, the project was aimed at compressible flow of a centrifugal compressor. Again, the measurement data is available, and also we have available one commercial code results to compare with. So complete centrifugal compressor characteristics were simulated and at 3 compressor speeds. And as you can see, the results are also in a good agreement. Okay, so this one is a detailed study we made on TCFD parallel scaling. So as you know, the scalability is one of the most important features of any CFD code. In modern CFD, it's critical for any CFD code to show the linear speed up with increasing of the number of simulation cores. Especially for unlimited CFD code like TCFD is, the scalability is crucial. So we made a detailed study on TCFD parallel scaling. The tested case was Francis turbine. The scaling results are amazing. Here you can see the key figures. And this study clearly proves that TCFD has very high parallel scaling efficiency. And of course, the detailed PDF paper is available for this study. So feel free to ask it to have a look at the details. Yeah, TCFD is being extended by the new applications. So recently we made TCFD able to simulate the external aerodynamics. We made a complex TCFD study on Spitfire aircraft. We found the CAT model and also the original measurement data to compare with the simulation results. So the agreement with the measurement was excellent. So again, the detailed paper of the study is available. So feel free to ask it. I will go ahead. Yeah, and in my last example, we have an optimization study. So we did this study together with our partner, a German company, Friendship Systems, who developed their product called Cases. So Cases is flexible CAD platform for fast and comprehensive design studies together with simulation tools. And together we made this study on fan optimization. And the optimization study is a cycle of many simulations of many designs. The designs were created in Cases and they were simulated in TCFD. And as a result, the engineer gets an optimized fan model with higher efficiency. So we did in this study, and again, the detailed paper of this study is available on request. Okay, I think this is it from my introduction part. So now it's time to hand over the presentation to Radek, and he will give you a live experience of TCFD workflow. Radek, are you ready for your part of the presentation?
Yes, I am. So, okay, I think you can see my screen, all of you. Perfect. So let me start with the second part of the webinar with the live example. So in this webinar, we will be focusing on a fun geometries, on a fun simulation. Although all the workflow I will show is also applicable to any other type of the turbo machinery, to all of the types of the turbo machinery which Luboš has already presented. So I will be showing the workflow on the several types of fan. So first one is this axial fan, simple geometry with one rotor segment or with rotor stage and stator stage. Then we will show you what is the difference to set up the same case, but only with the segment approach. So only one blade segment will be simulated. Then I have an example of radial fan. So how the setup is done, and to show some results or comparison studies, for example, for this particular geometry. And last but not least, because the latest version, the 18.10 version of TCFD, allows to define several rotors with different axis of rotation, different speeds. So also I will show you how to set it up. Okay, so let's start. So all these cases are our tutorial cases, so you can download it and you can try it by your own. So you can ask for the trial version, download the tutorial, for example, for this double rotor fan. You can download it here or in the download section and try it yourself. So let's start. So what we need at the beginning to start with TCFD. So for example, I've prepared an Excel fund segment live example. So at the beginning, we need to have the geometry in the STL format. So usually we need each component, which is the given part of your geometry, usually stator, rotor, pipes, and so are well defined and exported from your CAD software, for example, into STL format, which can be then used for TCFD setup. So this is all what you need. If you have already preset some simulation, all the setup is saved in TCFD file, which simply contains all the parameters for defining the setup of the TCFD simulation. Okay, and then you have two options. First one, just click the TCFD file or open the Turbo Machinery CFD. I have here several versions, but the actual one is 18.10. So I will open it. What I haven't mentioned now, I am in Windows, but the same workflow can be applied also in Linux, in Linux systems. So by clicking on TCFD file or opening the TCFD, you will see this graphical user interface, which is directly implemented into ParaView, which is a great tool for scientific data visualization or any kind of data visualization. And therefore, the connection between the setup of TCFD simulation and the post-processing, which ParaView provides, is amazing because you can do anything at one place. Or if you already set the simulation and you, for example, you are ready for optimization loop or any other loop, you can go directly to this preset case. You can open simply the command line, and by simple command, which is here. So I will just follow the TCFD installation. Okay, this is 10 binary, and there is the execution file CFD processor, which works very simple. Just you give him the setup file and what's to be done. So for example, I would like to write the case and create a mesh, for example, and additionally I can set, for example, where to store my simulation. So for example, my directory. Just click, just enter. You can put into your script or your scripting loop, and anything can be done without a graphical user interface. Okay, but now because I will be talking about the setup, so it is much more clever to use the graphical user interface. So this is how it looks like. So here are the several menus for the TCFD setup. On the right side, we have the render view in which both input geometry, then mesh when it's generated, and also the results can be visualized. Then there are several icons. For example, these icons are relevant for TCFD setup, and the other for some viewing options, for some application to the geometry, to the results, and so on. So I think it is quite intuitive, and it takes just several minutes to learn with the interface. Okay, so let's start with the TCFD setup. So usually you should go step by step over each menu and define the simulation, the TCFD simulation. So in the first menu, simulation type, it is distinguished to different type of turbomachinery or external aero, because each type consists of a particular setup tailored just for the particle type, as well as the evaluation or the post-processing tools are also tailored to particular case, including the efficiency evaluation and so on. So this is here. Inside the simulation, time management, so you can go for both steady state or transient simulations. Of course, you can set any number of processor which you have. There are no limitation. Numerical order first and second. The rule of thumb can be that you should, with your first case, with your first geometry, you should always go for the first numerical order. When everything goes well, then you can switch for the second order. Always it is problem dependent, so there is no common setup, but usually start first and then go for second. Then there are physics, so standard setup for fluid properties, dynamic, viscosity, and so on, density, and so on. You can enable compressible simulation or deactivate it. Then it is treated as incompressible simulation. Now, what is new in this version is the reference frames framework, which allows us to define several rotors. So for example, in this case, we have just two parts, two segments. So this is I think the flow goes from the left to the right now. So this is the rotor part, and this is the stator part. So I should define two frames. First one is static, to define the static frame, the stator part. It is not rotating, so no rotation speed is set, but the axis and origin of the rotational motion has to be set, because the solver needs to know the transformation to connect the segment parts, to build virtually to build a full wheel geometry. And the same for the second frame, which is rotating. So the name is up to you. You can define any name you want. And if you enable rotating, then you have to set the speed of the rotation of your rotor part. If I, for example, move to this double rotor fan, then you should define several frames. For example, the frame 2 is for rotating of this rotor part, and rotating 4, I guess, yes, is for rotating this purple part. So you can see also that the axis of rotation is nicely visualized. So if you make some mistake, you will be always informed that something is wrong, which is also a nice feature. Then the rest is almost the same. So you define as many reference frames as you need. Let's go back. And then we can go for the components menu. Basically here you define the mesh, the input geometry, and possibly and the mesh for the simulation. There are several options how to create the mesh. First one is to load the STLs files, which is this case, define the refinement, define the fineness of the mesh, and create the mesh by the SnappyHex mesh tool, meshing tool, or you can directly, for example, go for external Fluent mesh, and you can load the external mesh in Fluent format. So for those who are familiar with some external meshing software, you can go for that. So, but now I am switched to, I should go back to directory with STLs. So I need to load the case again, because when I switch to the external Fluent mesh, I have erased my setup. So this is two options. So STLs or external Fluent mesh. Then you can define here component name to be more clear which component is, or you can then know from report and any other setup that you are at the impeller or at the stator or any other part. Then what is important is to set a correct reference frame. So for rotating part, the first one is rotor. You should assign the rotating reference frame which you have defined in the reference frames, and the same for the component 2, which is the stator part. So here's the static frame. Then in case of the STL files, you just assign a correct type of the boundary. It is quite intuitive. For example, there are several types, but for blades, there is a blade type. For a hub, there is a hub. For the physical inflow into the domain, there are inlets or outlets. To connect for the connection between two components, neighboring components, you should go for outlet or inlet interface. And in case of the segment approach, you should define these periodicities and set the rotation AMI, and by right click you can connect them to make the couple, to connect these two periodicities. For example, if I go for the full wheel and go for the components, you can see that there are no connection because we have full wheel, so there is no periodicities to be connected. And as you can see, the other setup is the same. What I missed is the number of periodic segments. So for the full wheel, we have just one because we have full wheel geometry. But if we have only one segment, then you should set here the number of blades which builds the full wheel. So in this case, we have 20 blades on the rotor side. Okay, then we should define the refinement of the mesh. So first one, we have to set the background mesh size, which is basically the largest cell inside your mesh. So for example, to see how these cells are big compared to your input geometry, you can enable this show background mesh wireframe, and then you can see how rough or how fine it will be. So this is just case to be quickly computed. So I set quite rough mesh. If I go, for example, for this preset case, so the situation here is very similar. So show background mesh size, you can see it's more fine. What is also nice, and it will be also one of my examples, there is a setup which allows you to define a cylindrical background mesh, which is what is the background mesh? Background mesh is the initial mesh from which the final mesh is created, roughly speaking. And there is a cylindrical mesh options in which you can define a cylindrical background mesh. So for example, I can, for example, set some a little bit finer mesh. This cylindrical already defines you the topology of your mesh. So I will go, for example, for this view. This is nice. Then I can enable this parallel projection, which aligns me the background mesh with my geometry to be more visible, so we can see it. For example, here I can for example, make the background mesh a little bit darker to be much more visible. And now what I would like to show you, the cylindrical radii is the topology. So for example, I know that the radius of the impeller is 200 millimeters in this case. So I aligned with the hub. Then this cylindrical radii I will align with the sorry, this is shroud. So this one I will align with the hub. So I think hub is 140. Hope. Okay, this is this, and this I will put in the middle. Then this cylindrical grading. Okay, first I will start with cylindrical wrap. You can see that the topology inside goes to the circular shape. And to, for example, enable some boundary layer at the hub and shroud from the background mesh, directly in the background mesh, I can go for this grading. So for example, I will set here 5 and the inverse value on the other side on the shroud, and you can nicely see now that we have something like the boundary layer. And for this, I can then create the mesh. So I have some example here prepared in advance. So this is, okay, I will show background mesh off. So we can see this is, for example, the final mesh created from the hexahedral shape, and this one is from the cylindrical shape. So we can see obvious differences and so on. And this same we can done just for the segment in the same way. Then you can see this is a segment mesh created from hexahedral shape and is created from cylindrical shape. And at the end, we can compare the results at these different meshes and show what are the differences, for example. But let's move on. Let's move on. So these are components. I think I didn't forget anything, I hope. Yeah, maybe here the wheel diameter, which is the compulsory parameter for the efficiency evaluation for the fans. So you also have to define this parameter, simple wheel diameter. Let's go on. So components, then we have the speed lines. So speed line, what does it stand for? So speed line is a group of simulations which hold the same rotation speed. And for each speed line, so for one rotation speed, we can define several points to be simulated, usually with different flow conditions, with different pressure drop or volumetric flow rate for generating the full performance curve. Or for example, for compressors, we can define several speed lines with several points, and then we have within one simulation, we have the full performance map. So speed lines and number of points. Here we define the maximum number of iteration for each point. Then there is a turbulence model, so K omega SST, but you can go for your favorite or with that one which you have the best experiences with your particular case, particular project. Then the inlet and outlet boundary condition. Basically, here you define the flow conditions. So in this case, it is treated as a volumetric flow rate at the inlet and pressure, static pressure at the outlet, the kinematic pressure, because we are simulating it as incompressible. Then initial conditions, so some reasonable guess for the initial flow. Then there are simulation controls. So for more advanced user or for very specific cases, you can play around with the relaxation factors connected to the numerics, let's say. And then to make the solver more robust, you can define the bounding limits over which the values are bounded. If some, for example, oscillation at the beginning of the simulation appears, then these values cut these oscillation out from your simulation. So it makes the simulation more robust. And the final section is almost the final section is the post-processing, where you define the averaging window over which your simulation is average, because we are looking for average solution, as well as the stopping criterion somehow evaluated at in this window. Then you can choose your favorite units, both for pressure and mass flow, eventually for volumetric flow rate. Then stream path is just the path through your geometry, which plots the graphs from the inlet to the outlet. For example, for pressure drops or pressure values, total pressure values, velocities, and so on. Efficiency probes defines the places from which the efficiency is evaluated, usually from inlet or from outlet, and which torque patches you need to include to evaluate torques. For example, here is an example just for blades, but usually if in this case, for example, both hub and shroud are rotating, then we should enable both blades, hub, or all these patches to be included into torque evaluation. You can define more evaluation probes or places. For example, for this rotor part, if we have two rotors, we can define here two efficiency probes. First one for the first impeller and the second one for the second impeller. So you can also define, for example, efficiency probe to evaluate the efficiency from inlet to the outlet, or just at the rotor part, or just at the rotor and stator part, and so on. So it is very, very flexible. Then the forces. So I think this is not the proper case to show the forces evaluation, but for some for example, vane gates at Francis turbines, for example, the forces can be evaluated. Then blade-to-blade views and meridional average are some automatical evaluation and visualization tools, which are automatically visualized and generated. We will show them at the end, let's say, of my part. And also you can add some additional data files. So for example, if you would like to compare to your measured data to your previous simulations, you can put here file with the data, and the plots will be plotted inside the final report. Okay, I think it is enough. What I didn't say is that you can also enable the advanced options, which, for example, shows you this scripting part in which you can add the script. Usually we use it to follow our customer needs. So some of our customers would like to something special, so we develop a script which we implemented here, or which our customer put here, and do what what he needs, basically. So really some really advanced menu. Okay, so whenever everything is done, so I have several changes, so I will load my default case to be sure. Then we can go for this TCFD manager, which is a tool or framework for just simulation your preset case. You need to do just few steps. First one is define your directory in which everything will be stored. So for example, my second directory, let's say. So my second directory, then I have to write the case, so everything is preset, everything is stored to the disk and is prepared for the simulation. Then the second step is to create a mesh. So I have two options. I can run all button, which runs basically all meshing phase, simulation phase, and the post-processing phase, or I can do it step by step. So at this moment, I will click run all, and now the meshing is in process. And whenever it is done, this let's say this button or this column or this this part will be displayed in green, as you can see. And whenever everything is done, everything is in green, then TCFD goes for the simulation itself. During the simulation, you can follow, for example, the residuals, Meanwhile, you can, for example, visualize the mesh. So you can click here, show, then I will hide the components part, and basically you can here follow the mesh. Yeah, it is quite rough for this particular case, but it's totally up to you how fun you define and so on. Okay, and at the end of the simulation, so I will close it or I will keep it, but at the end the report is automatically generated. So I will show you the report. So this is my case. So I will go for some already simulated one. So for example, this axial fan simulation full wheel, and here you can anytime open the report, which is stored in this place, and will automatically appear in the graphical user interface whenever the simulation is done. So then here you will see the report. But now I will open it in this way, so you can see screenshot, let's say, of your geometry, then the basic simulation statistics, for example, rotation speeds, so some mesh statistics, y plus parameter, number of processors which were used for this simulation, time of the simulation, for example. Here in the graphs, you can see the process of simulation, both in volumetric flow rates and the residuals. And then the report includes several sections with a particular parameter which is evaluated. For example, fan characteristic, so some flow number versus compression number, efficiency. For example, here I have put some previous data. For example, these blue ones, this blue graph are the results for the case where only segment was simulated, and this one is the full wheel. The same for torque, for axial force, total pressure difference, total pressure per interfaces. So you can go for interfaces. So for example, to follow the total pressure at the impeller to stator interface, nicely see the values. Here is the profile path. So how the total pressure is changing from the inlet to the outlet or over each interface. The same for the velocity magnitude, circumferential and meridional angle, and last but not least are these automatically evaluated visualizations, for example, blade-to-blade views. So this is the blade-to-blade views with streamlines and velocity magnitude visualization. And I think the last one is the meridional average. So average to the meridional plane at the rotor part for each simulated point. Okay, so this is the report. Then I promised you some comparisons. So for example, what I have run in advance are four cases for this axial fan. So 2 cases for the full wheel geometry, one with the hexahedral background mesh, one with the cylindrical background mesh, and the same for the segment part. Then, for example, you can compare these 2 simulations. So I can show you here the report. So this is the comparison of simulation of the segment and simulation of the segment with the cylindrical mesh. You can nicely compare, for example, the number of cells, simulation time, and so on. So this report or this comparison report can be nicely and simply and also nicely generated by this TCFD compare options, which is very intuitive. So you can just click on it, load the HTML files of the wanted reports to be compared, and that's all. So you can compare, for example, residuals, and what we can follow is the flow rate versus efficiency. So you can see these are the difference between those types of meshes. Yeah, the same, for example, you can do for the full wheel geometry, so the same compare reports for the full wheel geometry. Again, we can go directly for the efficiency graph, for example. By clicking on it, you can make it larger and compare the result. For example, you can see that here are the differences much more lower than for the segment parts. And last but not least, I think I have something here. I have it here. So here I have prepared the compare of all my simulation for these Excel funds. So I can open it, and here is basically the comparison of the full geometry, segment geometry, and both types of meshes. And for example, again, go for efficiencies. So you can nicely then compare all your simulations, all your setup, and tailor it to your experience and so on. Yeah, so the flexibility is really, really large. Okay, and maybe if and this radial fan, for example, you can see that the simulation is very the same, the setup is very the same, 2 reference frames and so on. So almost the setup is almost very the same. Then you can again run the simulation. For example, here I have run several simulations with first order, second order, with 2 methods which I haven't yet mentioned. These MXP column defines basically the method of connecting 2 components. So first one is, if I set a 0, then there is a 1-to-1 correspondence, or basically it is a so-called AMI approach or frozen rotor approach. And if you set some positive value, then the mixing plane approach or a stage approach is enabled, which are two different approaches, which each of them has their own drawbacks and advantages. And what you can do is to run several simulations and to compare. So I have compared 6 simulations. One first numerical order, second numerical order, frozen rotor, stage or mixing plane approach, and mesh with layers and without layers, for example. And again, if we go for the efficiency graph, for example, here we can compare. For example, the purple one is the simulation with the first order frozen rotor. Then the green one is second order frozen rotor, and the light blue one is second frozen rotor, second order with the boundary layer. And for example, the method mixing plane or stage started with orange one, first order, then second order is the yellow one, and the second order with boundary layers is the dark blue one. So you can see that each setup influence your result. So you need to know which setup is the best for your particular design, for your particular project. So although everything is set up with the best practice, but each case, each project requires some advanced analysis to fit the simulation to the particular case. And this TCFD provides all these tools to make it happen. Okay, maybe I have also every visualization can be done directly here. So I have made here the comparison of, for example, of the case which has here, sorry, for the case which has the lower efficiency and the highest efficiency. And here you can compare it. So the lowest one is this one, so frozen rotor first order, and here is the simulation with the highest efficiency, 5 mixing planes second order. So you can compare visually the results. This is the total pressure, this is the velocity magnitude. For example, you can see that the mixing plane approach forces the, let's say, the rotational symmetry on the wheel. whereas the frozen rotor shows you really what goes from the wheel, it goes to the volute. So you can nicely compare both methods and decide what is the best method for you. So there are many tools how to do that. So TCFD really provides you all necessary which you need to have for a successful project. Okay, and I think I'm at the end. Yeah, the same for the double rotor fan simulation, and maybe I have just here one type of evaluation. For example, you can watch for mixing of the air for the both inlets and for the both rotors. So, for example, also this is possible to visualize. Okay, so I hope I didn't miss anything. So, Luboš, what do you think?
Radek, I think it's perfect. I think we can continue in the presentation. So I will take back the presentation. So here I go, and let's go ahead. So thank you, Radek, for your contribution. And now, yeah, we move to the Q&A session. So here we are waiting now for your questions, and we are. It's our pleasure to give our answers. So I would like to ask you now, please ask your questions, and we still have a few minutes in this webinar, so we will do our best to answer your questions, and if there will be some rest questions, we'll answer them via email. So please take this chance, use your time. We are here for you, and it's a pleasure for us to answer. So Radek, can you already see some questions you would like to answer? Maybe the first question from Chain is, hello, could you please tell me whether there are any materials for this webinar? So yeah, we will send this webinar recording to all of you, so you will have this recording, and also all these models or these geometries and axial fans and double rotor fan and centrifugal fan are there available online on our website, so you can easily go to the download section and download all these tutorials, and you can play with them as you like. So that's okay. Materials are available. If there will be any issues, feel free to contact us. We will support you. Maybe is there another question from Gregor? Hi. Yeah. In which graphical interface? I'm sorry. In which graphical program did you make the model? Yeah, so for general projects, together with TCFD, it's many times tested, and it's recommended to use Salome. We have very good experiences with Salome in general projects. In turbo machinery field, it might be reasonable to look for some specialized tools like CF Turbo or Cases. Those are our collaborators. Our collaborators are already on the way, so that might be reasonable to have a look for some special design tool which specializes in turbo machinery field. Okay, Radek, can you see any question you would like to answer?
Yes, I can. So if you give me the presentation back, okay? Because I will show my screen. So I will go for this great presentation and software of yours. Thank you very much. And what about such high Y plus values? It is just simplified mesh to get result in short time. Yes, for some particular case, yes, for dedicated just to this webinar. But for example, if we go for, okay, I will switch to some geometry, which is this one, for example, compare reports. So don't be scared about this value. So for example, this particular design has the y plus in the range for which the wall functions are dedicated, for example. And if you go for details, then you will see the average values for every part of the geometry, which is much more important, because this value is just the largest value from the whole geometry. So for example, in the outlet pipe, you don't, or inlet pipe, you don't need to have y plus too low, because it's just to initialize the flow, or at least at the outlet it is just to make the flow more steady for the boundary conditions, let's say, which CFD does like the steady state at, or steady flow, or not so turbulent and with many recirculation at the outlet. And for the radial fan, which was dedicated to this case, I think it is this one. Yes. So for example, although we can see here the large value, more than 700, but if you go for each part of the geometry, so for example, at the impeller blade section side is 280, which is somehow in the range, but you can see that there are some parts which is out of the range. So you can go back to the meshing part, you can mesh these parts to be more refined, or you can add the boundary layer or whatever. And for example, the case with the boundary layers, which is I think here, then you can see that the y plus are now in the allowable range. So this was the example how to iterate to get the mesh which follows the needs of the wall function, for example, and other needs. So click on the details, and then you can go really patch by patch, part by part of your geometry and check if the values are okay. And if not, you can go back to the meshing part, make that part more finer and simulate it again. Okay, what are the next questions? So Luboš, if you have one for the center, okay. Can cavitation be modeled, for example? Yeah. Okay, so I will answer this one, and then we can go back to Luboš. Can cavitation be modeled? What models are supported? Yes, it can be. And there is a cavitation model for the water turbines and water pumps. So just quickly, if I said here, let's say hydro turbine, it is only available for transient simulation, the full cavitation model, and then in physics, you can here enable this multi-phase cavitation, which is the full cavitation model by this Schneer-Sauer, using this Schneer-Sauer modeling. So yes, it is available. And okay, let's go to Luboš, which I think which just answers to some questions. So back to Luboš.
Okay, Radek, thank you. I think I'm just fine. We are approaching our time, so I think it will be our this will be it from us, I guess. We have I can see we have so many questions. We can by far we can't answer them right now. So I think this will be it. Anyway, it's 4 p.m. So the time is gone, and I will take the presentation back and let's conclude. Don't worry, all the questions will be answered later via email, so don't worry about that. Okay, so I think this is it from us in this webinar, and it's really time to finish. So stay tuned. Feel free to contact us. I'm sure you know how to do that. We will gladly support you in your projects. It's our job and also a pleasure. Anything more to say for the last, Radek?
Just let me thank all of you who are watching us, and I hope we have showed you everything important. And if you have any other question, or if you would like to contact us, or if you have some project which would fit TCFD, or at any circumstances, do not hesitate to contact us, and we will answer you. We can have a chat and follow what you need. So thank you, and bye bye.
All right then, so we leave you with that. So thank you for your attention. We are looking forward to collaborating with you, and stay tuned, and bye bye for now.